Hey, today we're going to talk about 9.7, Ocean Acidification. So before we begin, you can check out the Enduring Understanding, look at the learning objective, pause the video, review the essential knowledge, and set up your Cornell notes. So ocean acidification brings up a really sticky subject that students love to hate, and that is the concept of acids and bases. Remember that pH refers to the amount of hydrogen ions. It is a logarithmic function related to the concentration of H plus ions. So when you have a pH of 7, you actually have 10 to the minus 7, 0.000000001 molar H plus ions. And when you have a pH of 1, you have 0.1 molar H plus ions. So as you increase the amount of H plus, the solution is more acidic, and as you decrease the amount of H plus, the solution is more alkaline or basic. And when you have a pH of 7, your concentration or the amount of H plus and OH minus is basically equal. And this will balance it out, and this, because you have just as many H's as OH's, it is a pH of 7. That's just how it works out. Now, how it works out when you have a pH of 5 is you got 100 times more H plus than you did as a pH of 7. And when you have a pH of 9, you're going to have 100 times less H plus than you did when you were at pH of 7. Now, what does this mean? Well, in the ocean, which is predominantly water, there's other elements present, but we're just talking about water right now. And then you have your atmospheric carbon dioxide. So carbon dioxide is a gas, and it has a low solubility in water, but it's still soluble to some degree. So this reaction is actually reversible. When you add H2O and carbon dioxide, you will get, add them all up, okay, H2CO3. This is carbonic acid. Now, carbonic acid is what is causing, or which is leading to the ocean acidification. However, the problem is not necessarily with the carbonic acid, but it's what happens as a result. So carbonic acid is actually necessary to have in the ocean because it will release an H plus and leave us with bicarbonate. Now, bicarbonate doesn't really do us much good until it releases another H plus and gives us carbonate. Once you have carbonate, that carbonate is free to bind with calcium, which is a positive ion. This carbonate is CO3 with the -2 charge. This calcium is Ca with the +2 charge. Ooh, they could form calcium carbonate, which is limestone, which is the mineral that is necessary for shellfish, for a lot of invertebrates in the ocean, mollusks like snails and octopus, coral, lobsters, crabs, foraminifera, a lot of zooplankton and phytoplankton. All of those organisms can make shells with carbonic acid or with calcium carbonate. So this calcium carbonate is very important for organisms that are living in the ocean. Now, what happens is these H pluses don't just go and, they're positively charged, they're positive ions. They're attracted to a negative ion. So looking at this reaction, what do you see that's negative? Oh yeah, they could go back and bind with the bicarbonate, forming carbonic acid again. So it can potentially reverse this reaction. Also, they could both get together and bind with the CO3 and reform carbonic acid again. So if you get two of them can bind to a carbonate, and one individually could bind with the bicarbonate. Now, that's not normally a problem because there's enough of these ions present in the ocean. There's enough of them present that this cycle will, it will still produce calcium carbonate. However, once you add more carbon dioxide to the atmosphere, there is a lot more carbon dioxide that is mixing with the water. and carbon dioxide dissolving in the water, and then eventually forming carbonic acid and then releasing all of these excess hydrogen ions. So when you have all of these hydrogen ions, there's a very strong possibility that it will bind with one of these other ions. And the whole point of this is you want the carbonate to be by itself in order to bond with the calcium. So when you're adding more H pluses, you're basically pushing this reaction backwards. And that's a bad thing because it's preventing the calcium carbonate from forming. And if you prevent the calcium carbonate from forming, you could have a severe biodiversity loss because you will be making a lot of marine organisms, outside of their range of tolerance. And if the environmental conditions are outside of their range of tolerance, they will not survive, and that's what leads to biodiversity loss. So over time, over the last 30 years, we've actually seen an increase, and you know this, we've seen an increase of atmospheric carbon dioxide. So the concentration is now like above 400. I think it's like 412 maybe. It goes up every year slightly, but it's still going up. But we've also seen at the same time, we've seen the ocean pH drop from about 8.13 to now 8.09 or 8.095 maybe. But the oceanic pH is dropping, and that is directly related. So as you increase carbon dioxide in the atmosphere, you're actually lowering the pH because there's more H plus available in the ocean water. Okay, for FRQ practice, what I would like you to do is to identify a human activity that leads to ocean acidification and explain how the ocean acidification can threaten marine organisms. So I thank you so much for your attention. I hope that this video was informative. I will see you soon.